today, inshallah, we'll continue chapter 9. We'll talk in details about one-tail test. Last time we talked about two-tail test, and we discussed that there are three tools in order to test the null hypothesis. The first one is critical value approach. The second, p-value approach, and confidence interval. Keep in mind the last approach, confidence interval, is used only for two-tail test. So now for one-tail test, we are going to use two approaches, critical value and p-value approach. So there are in many cases, the alternative hypothesis focuses on particular direction. In this case, we have a certain direction. This direction could be to the left side. It's called lower tail test. And the other one, greater than or upper tail test. So there are two types of one-tail test. One is called lower test. In this case, the alternative hypothesis. Each one might be, for example, mu smaller than 3. So the null hypothesis can be written as mu is greater than or equal to 3. Just for simple notation, we can use mu equal to 3 instead of mu greater than or equal. So we can use this notation instead of using mu is greater than or equal to 3. It's better to use this notation because, as we know, h1 is the opposite of h0. So if under h0 we have mu greater than or equal to 3, then for the alternative hypothesis could be mu smaller than 3. But just to use simple notation, we may write mu equals 3 against the alternative hypothesis. Actually, we are focusing on the alternative hypothesis because the direction of this one gives the rejection region of the test, because my rejection region actually based on the sign or the direction under the alternative hypothesis. So again, this is called lower tail test. Since the alternative hypothesis is focused on the lower tail below the mean of 3. This is just an example. The other one, when we are testing mu smaller than or equal to 3 against mu is above 3, in this case, this one is called an upper tail test, since the alternative hypothesis is focused on the upper tail above the mean of 3. Now, how can we state the appropriate null and alternative hypothesis? The answer depends on the problem itself. So by using the problem, we can determine if the test is lower tail or upper. So we have to state carefully both null and alternative hypothesis. So for example, if the problem says increase, it means mu is above. If the problem says smaller than or decrease from whatever the value is, then we have to use mu is smaller than that value. Any question? So that's how can we state the null and alternative hypothesis for one tail test. Let's say in details the rejection regions for lower and upper tail tests. For lower tail test, so in this case we are focusing on the left side. So my rejection region should be this one. Now we are testing our hypothesis at level of significance alpha. For two-tail test, we split this alpha by 2 because we have two rejection regions, one to the right and the other to the left side. But here there is only one side, so one direction, so we have to keep alpha as it is. So we have alpha here. So they accept the rejection region below minus z alpha or minus t alpha. It depends on sigma, known or unknown. So it's the same concepts as we discussed before. So my rejection region is the area to the left side. So for this particular hypothesis, if we are talking about testing mu smaller than 3, then we may reject x0 if use this statistic or t same is smaller than minus the alpha. So there is only one rejection region in this case because we are talking about one tail test. So again, my critical value is only one critical value because here it's just one tail test and it's negative z alpha or negative t alpha. So we reject the null hypothesis if the value of the z statistic falls in the rejection region. It means that z statistic is smaller than minus z alpha. That's for lower tail test. For the upper tail, vice versa actually is the same, but here the rejection region is on the right side, on the upper tail. So here we reject the null hypothesis for the other case. If we are testing mu smaller than or equal to 3 against mu is above 3, the rejection region this area, so z alpha or above it. So we reject the null. So we reject h0 if my z statistic is above z alpha. So that's for lower and upper tail test. And actually, if z statistics falls below in this case, z alpha, then it falls in the non-rejection region. So we don't reject the null hypothesis. That means there is insufficient evidence to support the alternative hypothesis. So that's for one tail test, either lower or the upper tail. Let's see an example for upper tail test when sigma is unknown. Again, the idea is the same. Sigma is known or unknown. We just replace z by t, sigma by s. That's all. Here, for example, a phone industry manager thinks that customer monthly cell phone bills have increased. So he thought that the bills have increased. Now, by using this statement, we can figure out the alternative hypothesis. It's upper tail test. And now average over $52 per month. It says that he thinks that the customer monthly cell phone bills have increased. And increased means mu is above $52. The company wishes to test this claim. Here we are assuming the population is normally distributed. So first step, we have to state the appropriate null and alternative hypothesis. So based on this problem, we can easily figure out that we are testing mu smaller than or equal 52 against the alternative mu is above 52. So again, mu is smaller than versus mu is above. So this is step number one. So we have to form or to state the null and alternative hypothesis. So the mu above 52, it means the average is greater than $52 per month. Now suppose, for example, my alpha is 10%. And we choose a random sample of size 25. Now, by using this information, we can determine the rejection region. Now, the problem mentioned that sigma is unknown and the population is normally distributed. In this case, we have to use T. Now, my rejection region, since we are talking about testing upper tail tests, so my rejection region should be to the right side, T alpha. It's above. Now, T alpha, it means T 10% and degrees of freedom 24. I think many times we use the T table. So by using T table, you can find that your critical value is 1.318.
Yes.
So that's your critical value. Now, my decision is, if this statistic, if the value of this statistic lies in this rejection region, we reject the null hypothesis. So if this statistic above 1.38, then we reject the null hypothesis. So let's see if we reject or don't reject. So we reject the null hypothesis if your t statistic value is above or is greater than 1.318. Now suppose, for example, a sample is taken with the following results. N is 25. So we select a random sample of size 25. This sample gives an average of 53.1 and sample standard deviation of 10.
Yes.
Now, by using this information, we can determine easily the value of t statistic. So t stat, the formula as we discussed in chapter 8, x bar minus mu divided by s over root n. Here we replace sigma by s because sigma is unknown. Straightforward calculation gives 0.55. Now, after this step, there are two approaches to reach your conclusion about this example. Either use critical value approach or p-value. In this case, we cannot use the two-sided confidence interval approach. So let's see if this value, by using now approach number one, the critical value approach. In the exam, you don't have to use both, just use one of these.
Yes.
Unless the problem determines that you have to use the critical value or p-value or confidence interval. For example, if it is two-sided. Sometimes maybe I will ask you to solve the problems by using 3 different ways or 2 different methods, whatever. But if it's just solve the problem, you may use the critical value approach or p-value. So let's see now. For the critical value approach, one more time. Your critical value is 1.38. Now, as this value falls in the rejection or non-rejection region, now this value is smaller than 1.318. So this value actually falls in the non-rejection region. So since this step is smaller than, which is 0.55, smaller than 1.318, then we don't reject the null hypothesis. So we don't reject H0. That means exactly there is insufficient evidence to support the claim.
Yes.
And the claim is the mean is above 52. So your conclusion should be written by using this way. We don't reject the null hypothesis because or since this statistic is smaller than 1.318, that means there is not sufficient evidence that the mean bill is over $52. So that's by using a critical value approach. The other approach by using p-value. Unfortunately, t-tables don't give the exact p-value. So here we can use either Excel spreadsheet to get the exact p-value, or any statistical software packages might give the accurate result. But the tables we have gives the approximate p-value. If we have the table for this particular example, let's see how can we figure out the p-value by using the t-table you have. So let's open the T-table. It takes a second. So this is statistical table. So this is your T-table. Now we are looking for p-value at degrees of freedom of 24 because the sample size is 25. Now look at 24. So my p-value again. Your p-value is the probability of t greater than 0.55 because the t statistic is 0.55. Now let's compute this area above 0.55. Now if we have T-table, 24 degrees of freedom, we are looking for 0.55. The first value here is 0.685. Next one is 0.8, so it's increased. So my answer could be this p-value of 25, or we think my 0.55 is to the left of this value.
Yes.
So my p-value is to the left of this. Now here, as t statistic increases, p-value decreases. So vice versa, there is inverse relationship between t-value and p-value. Now, 25 to the right, 20, 15, so the values are decreasing in this case. So what do you think? My p-value is above or smaller than 25? Above. So your p-value in this case is greater than 25. Again, T-table does not give the exact p-value, so just you can say my p-value is above 25%. Always, as we mentioned before, we reject the null hypothesis. Always, we reject x0 if your p-value is smaller than null. Always. Now, this rule does not depend on the alternative hypothesis. Always, we reject the null hypothesis if my p-value is smaller than null. Now, does this p-value smaller than alpha of 10%? Now, my p-value is above 25, greater than 0.25%. So this p-value is above 10%. So we have to reject if p-value is smaller than alpha. In this case, p-value is greater than alpha, so we don't reject the null hypothesis. Make sense? Now, the exact p-value is 0.2937. T-table gives this result, greater than 25%. The exact is 0.2937. Again, since my p-value is above 10% or greater than 10%, so we don't reject the null hypothesis. Now let's see how can we use Excel to find the exact p-value. I will use Excel to find the exact p-value. Here you may press on function. Then we have here T distribution. X, it means the value of the test statistic. In this case is 0.55. Degrees of freedom, 24. Tails, we are talking about one tail test, so it's 1. So here, just write the value of the test statistic, degrees of freedom, then 1. Now, the exact p-value is 0.2937. So that's the exact p-value. Exact answer equal 0.2937. So either one will give the same conclusion. It's 2.937. or greater than 25%. We reject if p-value is smaller than alpha, but this p-value is greater than alpha, so we don't reject the null hypothesis. So we end with the same conclusion. Actually, this slide gives how can we use t-test, how can we use Excel sheet to find the value or the find of p-value. That's all for testing about the population mean. If sigma is known or sigma is unknown for two-sided test or one-sided, upper or lower-sided test. We mentioned before that there are two types of testing. One is called hypothesis testing for the mean, and the other for the proportion. Because, as we mentioned before, there are two types of data. One is the numerical data, which is quantitative, and the other is qualitative data. Now, for numerical data, we have to use the means. Otherwise, if the data is not numeric, if it is qualitative, we have to use proportion. For example, if we are talking about gender, so it's proportion we have to use instead of the mean. Let's see. Now, if we have a data on gender, gender is classified males and females. Suppose, for example, there are, and you select a random sample of size 100, and you are interested in number of female students. And the sample has, for example, 46 females. So now your proportion is x divided by n. 46 divided by 100, so 0.46. You cannot say, for example, the average of gender, for example, is 1.3. It has no meaning that the average is 1.3. You have to say that, for example, males or females represents 46%. Rather than saying the average, for example, is 1.3. This one has no meaning. So if we are talking about two possible outcomes, success or failure, switch on, switch off, a good item, defective item, and so on, we have to use a proportion instead of the mean. Here we'll talk about in details about hypothesis testing for proportions. So in this case, your problem involves categorical variables. It means we have classification, either yes or no, males, females, and so on. So two possible outcomes, possesses characteristic of interest. So suppose I am interested in number of defective items that is produced by a firm. So my interest here in this case is number of defective items. So number of defective items is your X. So for example, suppose the firm introduces 1,000 items, and we found that 10 of them are defective. So the proportion of defective in this case is X over N. And we are interested in the population proportion, as we mentioned before, is pi. So pi is the population proportion. And actually, this P or pi ranges between 0 and 1, so never exceed 1 or below 0. So again, this slide actually is the same as we have discussed in chapter 8. Sample proportion is P. P is X over N, and X is the number in category of interest in sample. N is the sample size. And we know that if the two conditions, N pi and N times 1 minus pi, are at least 5, then B can be approximated by normal distribution with mean equal pi and standard deviation equals square root of pi 1 minus pi divided by n. So actually this slide is repeated. So again, your B value, your proportion is approximately normally distributed of mean equals pi and sigma pi 1 minus pi divided by n, all under square root. Now, based on this sampling distribution of P, what's your Z statistic? As we mentioned in chapter 6, the standard formula for Z statistic is x minus mean of x divided by sigma of x. This is the standard formula for the Z-score. In chapter 8, there are two cases. One is the mean, as we mentioned. So in this case, if we are talking about the mean, so we should have x bar minus the mean of x bar divided by sigma of x bar. So similar to this one, but here we replace x by x bar. From chapter 8, we know that the mean of x bar is mu, and sigma of x bar is sigma over root n. Now, for this proportion, your Z statistic is again replace x by p minus mu minus p divided by sigma over p. So b minus. The mean of p is pi. So this is pi. Divided by sigma root pi 1 minus pi divided by. So this is your Z statistic. So actually there is nothing new. We just repeated the concepts from chapter 8. So this is your Z statistic, P minus pi divided by root pi 1 minus pi divided by the sample size. That is valid only if the two conditions are satisfied, which are n times pi at least 5 and n times 1 minus pi is at least 5. If at least one of these conditions is not satisfied, then we cannot use the Z statistic. So there are two cases. If the two conditions together satisfied, then we have to use Z statistic. Otherwise, if one of the conditions is not satisfied, then we cannot use the Z statistic. This case not discussed in this chapter. So that's all for testing about proportion. There is an equivalent form of this statistic. We may replace B by X. For example, we know that B equals X over N. Now let's see if we multiply N for the numerator and denominator. So if we multiply N here and multiply N for both, let's see. I will reach another formula for this statistic. The first one depends on the sample proportion. The other one will depend on X. Now, N, this one equals N times P, which is X, minus N times pi, N pi. So again, N times B is X, minus N pi. Now N under square root becomes N squared. So N squared, we have N, so 1 cancel. So N is left, so we have N pi 1. These two statistics are equivalent. So you may use B minus pi. Frequently, the common one actually is this one. B minus pi divided by root, square root of pi 1 minus pi divided by N. So actually these two forms are equivalent. In this case, the two conditions, x is greater than or equal 5, and n minus x is at least 5. Let's look at this specific example. A marketing company claims that it receives 8% responses from its mailing. So now the claim is the company receives only 8% responses from its mailing. So from their records, we know that the proportion of response is 8%. To test this claim, a random sample of 500 were surveyed with 25 responses. So we are actually interested in the number of response. So x is 25. So this survey of 500 gives 25 responses. Now test at 5% significance level. Now the direction is not given, just y equal 8%. So we have to test h0 against h1 of y does not equal, since the direction is not given. This problem does not say it's above or greater or decreased or increased. So it's two-tailed test. So we are testing if 0 y equals 0.08 against the alternate hypothesis mu is not 0.8. Now the first step we have to check the two conditions. N times y. N is 500, y is 8%. So 5 times 8 gives 40. Now the other condition is the complement actually. So since n equal 500, so this one should be 460. The reason behind that is if we add ny and the other condition, n times 1 minus y, so this gives ny plus n factor here, n minus ny, so this cancels, so we end with n. So the total should be 500. So if the n times y is 40, then n times 1 minus y is 460. So two conditions are satisfied. Then we can say that the sample proportion is approximately normally distributed with mean equals y, with standard deviation of square root pi 1 minus pi divided by n. So that's your mean. So the mean is y, and sigma root y is 8%, times 1 minus pi is 98 times 2 divided by n 500. So your z statistic p. Now what's the value of p? P equals x over n. X is given, x is 25, divided by 500, so p is 5%. So now, z statistic, p minus y, divided by this sigma, which is 0.892 divided by 500. This will give minus 2.47. So straightforward calculation gives value of negative 2.47 for the value of the test statistic. Now, let's look at three different approaches to solve this problem. Number one, critical value approach. Now we are talking about alpha of 0.5%. So my rejection region is minus 1.96 to the left side and 1.96 to the right side. If the value of the statistic falls in one of these two rejection regions, then we have to reject the null hypothesis. Now this value actually falls in the rejection region to the left side. So since this term equals negative 2.47, smaller than negative 1.96, so it means the value of the test statistic falls in the rejection region, then my decision is reject F0. So again, your Z statistic, negative 2.47, falls in the rejection region. So my decision is we reject the null hypothesis. That means there is sufficient evidence to reject the company claim of 8% responses rate. So this claim actually is incorrect. So we have to reject this claim. It means we have to support the alternative hypothesis. So we end with this result. That is pi is not 8%. So that's by using a critical value approach. Any question? Let's compute B value for the other approach. Now in this case, we are testing two-tailed test. So your B value may be greater than or smaller than. So we have to compute one of these two, then multiply the answer by 2. Because the area to the right of 2.47 equals the area to the left of negative 2.47. So now, by using the ideas from chapter 6, let's see how can we compute your B value. Again, we are talking about two-tailed test. So your B value is probability of Z greater than 2.47 or smaller than negative 2.47. Now, the table we have gives the area to the left side. So it's better to use Z smaller than. So now by using T-table, B of Z negative less than negative 2.47, let's look at the table for the normal negative side. Look at negative 2.47. Negative 2.4 all the way under 7, we will get this result. So 0.068. So this is one of the two areas. So the area below negative 2.47 is 0.068. The area above the same value is the same area because of symmetric. So it means that just multiply this by 2, you will get 0.0136. Now, always, as we mentioned before, always we reject the null hypothesis if your B value is smaller than alpha. Now, alpha is given by 5%. Now, is this value smaller than alpha? The answer is yes. So, since my B value equals 0.136, smaller than 5%, then again we reject the null hypothesis. So we end with the same conclusion by using the critical value. That's for using B value approach. So here we reject the null hypothesis since your B value is smaller than alpha. The last approach, which is not given in the slides you have, critical value. I'm sorry, confidence interval. And we know that confidence interval approach P plus or minus Z square root P 1 minus P divided by n. B is 0.5 plus or minus 196 times 0.5 95 divided by n. Let's compute the the two limits. So we have this value here represents the margin of error. So let's compute the margin of error first. So it's 1.96 times square root of 0.5 times 0.95 divided by 500. So the margin of error is 0.19. So 0.5 plus around 0.102, around 0. For example, let's say it's 0.2. It's approximately 0. So now the confidence interval for pi, so 95, confidence interval of pi is pi greater than or equal 0.5 minus 0.2 is 3%, and the plus 2 gives 5%. So now pi, the population proportion, falls between 3 and 7%. So your range here from 3% all the way up to 7%. That's pi. Now, we are testing about x0, pi equal 8%. Now, is this value lie below, in the interval or outside? This value actually lies outside this interval, so it's never equal 0.08, because pi in this confidence interval ranges between 3% all the way up to 7%. Now, does 8% lie in this interval? The answer is no. That means it never equals 8%. So we have to reject the null hypothesis. So since the confidence interval we have does not cover or capture or contain pi of 8%, then we reject the null hypothesis. So actually, there are three methods to solve this problem. One is critical value approach, and in this case, we just found the critical values here, minus and plus 1.96, and the value of the statistic, this statistic I mean, falls in the rejection region, so we reject the null hypothesis. That's for the first approach. The other one, the p-value, and we found that the p-value is 0.136, which is smaller than alpha. Yes. Then again, we reject the null hypothesis. The last approach is the confidence interval approach, because here we are talking about two-sided test. And the confidence is approximately by ranges between 3 and 7%. And my pi, which I am talking about, the null hypothesis, is not in this interval. I mean, the confidence interval does not capture the value of pi of 8%. Therefore, we reject the null hypothesis. That's for testing about population proportion. Any question? Next time, inshallah, we'll start chapter 10. Up to this point, we just explained hypothesis testing about one sample. So there is only one sample in chapter 9. Here, suppose there are two samples. How can we conduct hypothesis testing for comparing two population means? For example, suppose we are teaching males and females, and we are interested to see if there is a significant difference between the performance of males and females. For example, suppose the instructor claimed that males do better than females in the exam. So how can we test if, for example, the mean score for group A, for example, is greater than the mean of group B? So in this case, there are two samples. So how can we conduct hypothesis testing for two sample tests? That will be in chapter 10. So chapter 10 left for this course. In addition to that, we will discuss correlation and simple linear regression after that. So maybe we'll discuss two more chapters, 10 and 12. If we have enough time, maybe we'll cover chapter 11, chi-square. It depends actually on the time we have. So that's all for today. Any questions? Comments?